Alright, we're going to make another video. This one happens to be about something I lost decades ago. Potential. What we're going to deal with then is just reminding you that, hey, sometimes electrons move against an electric field, in which case you have to do work and push them. Sometimes they move with the electric field, so the field does the work, in which case it'd be negative. And so we had these notes before where you can kind of quantify-ish how much work it would take to move an electron with the field or against the field. Just remember, the electric field is defined as the direction a positive charge would go. The charge you're moving through the voltage is how you can calculate work, Q delta V, if it's not involving kinetic energy. What that means is if the charged particle is stationary, then you pick it up and move it and place it somewhere else where it's not moving again. You can calculate the amount of work it takes by the Q delta V. Please realize in this example they are the same sign. The amount of work that is done is the same sign as the amount of Q delta V, that change in energy. Voltage then is the amount of potential per charge, okay? Potential energy per charge, Q delta V, and it led to these units. A volt is a joule per coulomb. A joule then is a coulomb times a volt. And with that, we said, well, gosh, we could take a different unit for energy, a joule instead of a coulomb times a volt. We can say, well, what if you're moving just simply a number of electrons times a volt, in which case you get a unit of energy called an electron volt. Okay? And that also then introduced us to ED, parallel plates, where you have a very uniform electric field between parallel plates. The amount of work it would take to move a charge from one plate to another is simply Q delta V. Now remember, work is force times distance. All right? Since an electric field is the Q is force per charge, then the force is the charge times the electric field. It's just the force, the Q times E. So where that F is, I can put a QE, multiply that by the D. That equals the Q delta V. The Q's die, and the change in voltage is equal to ED, where we once again say hi to ED. That then is only true if the electric field is constant, like between two sets of parallel plates, which we will talk about capacitors in a bit. But remember, this delta V equals ED is a place to start. Like we said with ED here, what I would like you to remember again, voltage is the electric field times distance. Remember that electric field formula, KQ over R squared. All right? If I take that electric field and multiply it by a distance, please realize that that distance is a radius. All right? So what that ends up being is saying the voltage is simply KQ over R, and it's not squared. So if I want to know the voltage a given distance away from a fixed charge, then all I do is take KQ over R. And that voltage then is a measure of, loosely speaking, how positive is it when you are a certain distance away from a charge. So if you have a positive charge, that positive charge is radiating out in all directs, y, and zetians, and it gives potential, or it gives voltage to that region based on how far you are and how strong it is, okay? So voltage is KQ over R. It is very similar to the electric field formula. Just multiply it by however far you are from the object creating that electric field. That'll be the voltage there. Work then is also energy, which is again a force times distance. That was also brought to you a little while ago by ED. So if work is force times distance, the electric force between two objects, you know, is K times the two Q's divided by however far they are apart from each other. All right? If I take that force, multiply it by a distance, then however far apart they are, that D is again an R. So that D will kill the square of that R, and you have KQ over R, which is what's left there, multiplied by the Q, KQQ over R. Okay, so it's the same formula, KQQ over R. but not squared, all right? This KQ over R, I want you to recognize, is the voltage formula. That's the amount of energy that is given by the field itself. If you're going to move a certain Q through that electric voltage, that Q delta V, then this Q delta V is work, all right? Because that KQ over R is voltage. And so Q times V is the amount of work. That gives you changes in potential energy, and some of you know that potential energy is abbreviated by a U. See? And something else that we can then deal with in terms of units. An electric field, you know, is a force per charge, F per Q, newtons per coulomb. That's the way we can communicate how strong an electric field is how many newtons does it exert over any given coulomb. All right? With Ed also, we can say, well, gosh, Ed is a volt, right? The electric field times however far you are from that electric field, the item exerting it, is your voltage potential. So the electric field, again, is a newton per coulomb, what we just said, times a distance now is a newton meter per coulomb. Well, hopefully you recognize a newton meter is a joule, so a joule per coulomb is how we define what a volt is. All right, a joule per coulomb is how we define a volt. Joules per coulomb. Now, if we rearrange Ed to say E is simply the voltage divided by the distance, then you can also communicate the strength of an electric field not only in newtons per coulomb, but you can say it's the same thing as a volt per meter. It's a V per M. So volts per meter is exactly the same thing as a newton per coulomb. They look strikingly different, which is why they're identical. The way we can remind ourselves or show ourselves that is, remember, a joule per coulomb, that's a volt. I can rearrange that and call it a coulomb is the same thing as a joule per volt. So all I did is have the V and the C swap places. Now what I'm going to do is take that version of this formula, plug it into my electric field strength as a newton per coulomb. And now you can see a swappertuna C, where this C is the same as that C. So where that C is, I'm going to replace it with a joule per volt. So it becomes a newton per joule per volt. I can then simply flip that denominator, and it becomes a newton volt per joule. And again, remember, a joule is simply a newton meter. So then it becomes a newton volt per newton meter. The newtons die, and that is a volt per meter. So, okay, it's just weird. A volt per meter is the exact same thing as a newton per coulomb. Huh? Fascinating, I tell you what. And that then, again, also shows you some of these formulas here on this second part of electric potential notes that we're going over KQ, Q over R squared, that's a force. And the electric field is KQ over R squared again. That volts, take that electric field, multiply it by however far you are, and that is going to kill the square of the R, and you got KQ over R. Remember, volts and potential are energy, or is energy, so they are not vectors, all right? So they're not. We don't triangulate them. This is an example of a type of question that they might ask you in terms of calculating work in moving charges from one point to another. So we have point A and point B. Those 2 points are located inside electric fields given to you by Q1 and Q2. Q1 is positive 45 microcoulombs. Q2 is negative 30 microcoulombs. Those 2 points are separated on an axis by 36 centimeters, and point B is smack dabber in the middle. Point A is on a y-cis 13 centimeters below Q1. And the type of question that is very typical you'll see is how much work is done in moving a certain amount of charge from one spot to another. So from point A to B, it'll be a positive 7.5 nanocoulomb charge to go from here to there. All right? So something I'd like you to then realize is it's simply a Q delta V question. All right? It's just work. Q delta V. Well, what's the delta V? The delta V is the voltage at point B, your final voltage, minus the voltage at point A, your initial voltage. How do you know what the voltage is at any given point? Well, at point B, just add up the voltages that are there courtesy of the two charges. So at this point, there is a voltage brought to you by Q2 and a voltage brought to you by Q1. At point A, then, you'll subtract that from it because that was your initial starting location. At this point, there is a voltage brought to you by Q1 and Q2. So you just simply take the amount of Q that you're moving, multiply it by the delta V, which is expanded as to say the sum of the voltages at point B, which means the voltage due to Q1 at point B, plus the voltage due to Q2 at point B, and I will subtract from that the voltage due to Q1 at point A and the voltage due to Q2 at point A. So I will subtract that sum from this, multiply it by the Q. That's the amount of work that is done in moving that amount of charge. So work, again, Q, voltage, the delta V, voltage, KQ over R. KQ over R. So this is R. That is from B minus A, final minus initial. So B minus A, and the formula for voltage is KQ over R. So the Q brought to you by charge 1 divided by the distance, the radius, that 1 is from point B, plus KQ2, and divide that by the distance, the radius 2 is from B. From that I will subtract the K, same Q1 divided by how far it is from point 1, from A, charge 1 from point A, and the KQ2, the same Q2 divided by the radius that point 2, or that A is from charge 2. Now that's the only one you got to Pythagorate, all right? The distance from 2 to A is the only one you need to Pythagorate, because this distance is a straight line, that distance is a straight line, that distance is a straight line, and so is that one too, but it's at an angle, so we're going to have to Pythagorate to get that one, and it's just 0.13 plus 0.36 squared, square rooted, it's 0.13. Now, when you solve these, you simply fish out the K, and if you wish to distribute the negative sign, you can. It just depends on how you want to type that problem. If you want to distribute that negative to here and here, you can, and then get rid of those parentheses, or if you want to keep it as is, leave the parentheses in when you do the typing, it just depends. So the amount of Q we are moving, 7.5 times 10 to the negative ninth. So 7.5 nanocoulombs times that K that I fished out, 99 Newton meter squared per coulomb squared. All right, Q1 is positive 45 times 10 to the negative 6 coulombs, and it was 0.18 meters away. To that I'm going to add the voltage due to point 2, or charge 2, the negative 30. All right, keep the sign here. It is negative 30 times e to the negative 6. It's also 18 centimeters away. From that I'm going to subtract. So I didn't distribute the negative. I left it as is, keeping these parentheses there. All right, so when I typed it, I didn't distribute the negative, but if you wish to, you can. Just then don't type the parentheses. So it's 45 times 10 to the negative 6 divided by 13 centimeters, plus then that negative 30. Again, that's the same Q2, negative 30 times 10 to the negative 6 divided by how far that is. And remember, the denominators are not squared in this. When you do the math, I promise you will get negative 0.0124 joules. All right? Now, that negative, again, can be a little confusing. And the reason I went ahead and wrote these numbers down here, this quantity is where you ended. This much potential, 8.33 times 10 to the negative 5th. All right, that negative 5, we then compare to the amount of potential that you started at from A to B, right? So final minus initial, you started here. 2.680 negative 4, all right? That negative 4 means you are literally more positive here than you are there, which means at point A, when you are 13 centimeters away from a positive charge and 38 centimeters away from a negative charge, then you have a greater positivity, a greater degree of positive. If you're hanging out at point A and I ask you, how positive is it? You would answer with the number you calculated for the voltage at point A. when you move to point B, this is a lower voltage for two reasons. One, you're farther away from the positive charge, that's Q1, and you are closer to the negative charge, that is Q2. So if I were to ask you, how positive are you at point B, you would respond with the voltage at point B, which would be a lower number than it was at point A, which is what we can clearly say right there. That E negative 5 is a smaller number than E negative 4. So then what I want you to then realize is, what does a positive charge naturally want to do? It wants to move from a high voltage to a low voltage. That's what it wants to do. It wants to decrease its own energy. It wants to do that. So this positive Q wants to go towards the more negative location. It simply does. And when it does that, it loses potential. So here's another example where I'm going to say that work is the negative change, or is the change in potential. It's the same sign in this example, all right? Work is change in potential. These are conservative forces. It's all internal. The field and the electron, just what's physically happening, or is that charge is being moved, and as it's being moved, that amount of work is changing its potential by the same amount. So the work is the Q delta V. There's no negative sign between them in this particular example. All right? Now, remember what we said about Ed. Ed says that, hey, if the electric field is constant, then you can use these. Only if the electric field is constant can you say hi to Ed. All right? Like between parallel plates, which will be the basis for capacitors here in just a few. But what I did is went ahead and I'm going to show you what calculus examples happen if the electric field is not constant between two places. Then what is the voltage at a particular location? So if that electric field is not constant, then between two spots, if it gets weaker with distance, which they do, or what the voltage is a certain distance away from something, this is a way that used calculus to get there. Remember, work is Q delta V. Q delta V, again, is the same thing as Ed. Multiply that by the cosine and the distance between them. So a Q delta V is the same thing as, I don't know, a delta V is Ed. I put a Q in there, didn't need to, but Ed cos theta. Remember, the electric field and the distance that an object is being moved, they are in the same direction or the exact opposite direction, but the cosine of theta is either 0 degrees or 180 degrees. And so if it's 0 degrees, the cosine of 0 is 1, and so we'll take Ed and multiply it by 1, which means we just have Ed. So the Q delta V is Ed. Delta V, VF minus VI is ED. If that electric field changes with distance, then what we'll do to get the voltage at any given location is say, well, gosh, let's break that distance into differential distances. So we're going to have a DD. See? So the VF minus VI is the electric field, which will stay constant at a particular very, very short difference in distance. And that differential distance we will call an R, because it is a radial distance outward from a fixed charge. So a radial outward distance from a fixed charge. So if we start at an infinite distance away from something, and then take that something, and how much work would it take to move a particular charge from an infinite distance away, closer and closer and closer and closer to a certain position R from a point charge. That's what we're going to do. So we're going to take an imaginary hypothetical Q, an infinite distance away from a fixed point charge, and say how much work would it take to get it there. That work then is a Q delta V, which is the same thing as an E D, and so that is what we will use to calculate that work is Q delta V. All right, now here's again where it'll be a little different from last time. Since something external will be pushing that charge, right, then the work that one item does is opposite of the amount of energy gained, the Q delta V. So again, if I'm doing work, that object is gaining or losing energy. So here where is an example where the work is a negative Q delta V, as opposed to what we set up here, where work is not the negative Q delta V. All right, so we have negative Q delta V is Q, the amount of charge we are moving, times the electric field we're moving it through. So the electric field we're moving it through, the Q that is being moved, that hypothetical imaginary Q, which dies anyway in this example, times a differential distance or radius. All right? Now, that delta V is a VF minus a VI. If you are an infinite distance away from something, then you have zero desire to interact with it. So that potential is zero at an infinite distance. So that VF is what we will end up calculating. It is going to be the negative version of Q delta V. In this case, that's E dr, the negative electric field times those differential distances that we're going to say the electric field is constant over very, very, very small differences in distance. And we're going to go from an infinite distance to a specific radius, however far away we are from it. All right? So this is the initial setup here. VF minus VI is equal to the negative integral E dr, starting at an infinite distance, ending at however far away you care to. All right, so here again we got a VF is equal to the negative infinite distance from R, E dr. Okay? Now, that electric field is going to be constant, but again, it's KQ over R squared. That's the formula for electric field. All I did is substitute that in there, dr. I'm going to rewrite it to look like this, KQ R to the negative 2 dr. When I do that, also remember I can fish out the K and the Q, because those two are going to be constant. K never changes. Capital Q is the amount of charge that's fixed in place. That is whatever it is. So outside that integral now, I have a negative KQ. So what I then integrate is R squared, R to the negative 2. Simply becomes R to the negative 1 over negative 1. And I go an infinite and an R. Okay, so that final voltage is negative KQ, and I wrote it as 1 over R, so it'd be easier to see, 1 over this now. That R is in the denominator, but when I divide it by negative 1, that brings that negative 1 there. So it's negative 1 over R minus negative 1 over infinity. Now 1 over infinity is pretty darn small. I'm going to call it nothing. So this negative then will kill that negative, and I get KQ over R, which should make sense. That's the voltage. This way you obtain it is something that you might bump into on occasion in certain tests, or show that the voltage at any given distance from a point charge is KQ over R. All right, the voltage in any fixed, it's the same sign as the charge causing it. All right, it's the same sign. So if it were a negative Q, then the voltage would be a negative. So sometimes you have a negative amount of potential. That's if it's coming from a negative charge, because again, voltage, loosely speaking, is how positive is it? I don't know, but that voltage then is what will tell you that, okay? So hopefully that helps. I don't know, but that's a little bit about potential. And hey, yay, physics. Bye.